Let's explore what we would see if we approached the speed of light. Imagine embarking on a spaceship that accelerates away from Earth, moving faster and faster. What would we observe during constant acceleration? What optical effects might occur? And if we tried to exceed light speed by bending spacetime, like in sci-fi movies, what would we see? Answering these questions will immerse us in the fascinating phenomena of our universe and take us to the heart of special and general relativity. Our spacecraft is initially at rest. Take off. Once launched, we begin to accelerate. We imagine that its propulsion system allows us to accelerate constantly for as long as we wish. As we gain speed, we move away from Earth, accelerating more and more. One might think that the speed would eventually become unbearable. However, this is not the case. Speed has no effect on our body. When two trains cross, it's impossible to feel whether our train or the other is at rest. Similarly, inside the spaceship, we cannot feel its speed, only its acceleration, the thrust of the reactors, which presses us against our seats. If this thrust is reasonable, it will be perfectly bearable throughout our journey, even when approaching the speed of light. There is, nonetheless, a risk associated with very high speeds, a collision. At high velocity, even a mere speck of dust could cause colossal damage if it hit us. Fortunately, our ship is equipped with a force field that repels dangerous objects, allowing us to roam freely through space. As we accelerate, the first optical effect, known as the aberration of light, appears. The stars in front of us, which we approach, seem to gradually move away as the sky contracts before us. To understand this, think of a common situation. You're in a car driving at high speed, and it starts to rain. The rain falls vertically from top to bottom, but as the car moves forward, you receive raindrops on the windshield from the front. The rain no longer appears to fall from above but from the front, as if its trajectory were tilted. The more you accelerate, the more the rain seems to come from the front. In our spaceship, the optical effect is perfectly analogous. The star's light comes from a certain direction, but as we accelerate, the light rays appear to come more and more from the front, as if their direction were different when we are in motion. This is the aberration of light. As light focuses in front of us, its intensity increases, while behind us, the sky seems to widen and become darker. The aberration of light results in another strange phenomenon. Imagine we are moving through an immense grid representing the fabric of space. Ordinarily, we would see a straight grid made up of straight lines converging in front of us due to perspective. However, by speeding up, the aberration phenomenon distorts the image of the sky around us. As the days go by, the grid seems to contract forward, and the straight lines bend. If we were to pass by an object, it would appear slightly angled in our direction. This is called the Terrell-Penrose rotation. As we move very quickly, images of objects seem contracted in front of us, and perspective is strongly distorted. We often hear that the farther we look into space, the farther we look into the past. Indeed, the light we receive from a distant star must travel billions of kilometers. This journey is not instantaneous, and it takes some time for light to reach us. As a result, we see the star as it was in the past when it emitted this light, perhaps several thousand years ago. Who knows how it might have changed since then? Looking out from our spaceship, the same phenomenon is at work. As we move away from Earth, the planet's light takes longer and longer to reach us. If we could zoom in with a telescope, we would see people on Earth evolving in slow motion. This is the Doppler effect. Each tick of the clocks on Earth takes longer and longer to reach us. We receive light rays in slow motion, and their intensity seems to weaken as the image of the planet shifts towards the red color. In front of us, it's the opposite effect. The ship catches up with the light, and the stars seem to get brighter, shifting towards blue color, with their clocks ticking faster. With precise enough equipment, we could measure the aberration and Doppler effects since the start of our acceleration in space. However, if we decided to end our journey and return to Earth, these effects would have had no impact. They are only optical illusions due to the way we receive light while moving. After several hundred days, however, as the reactors push us ever faster, the ship begins to approach light speed. At such speeds, some phenomena will no longer be mere optical illusions. Real physical effects will kick in with irreversible consequences. Special relativity comes into play. A first consequence of relativity is known as time dilation. Our universe is a huge four-dimensional fabric called space-time, made up of 3 dimensions of space and 1 dimension of time. Inside space-time, all bodies trace a trajectory since they all advance towards their future. Before takeoff, our ship was moving in the same way as Earth, towards the future. But by picking up speed and zooming away from Earth faster and faster, our trajectory gradually deviated from that of the planet. The axis we call time is no longer aligned with the time axis of people on Earth. If we decided to turn around and come back, our clocks would have measured a different time, and we would have aged less than Earthlings because our trajectories in space-time would have been different. Another key consequence of special relativity is called length contraction. When a body moves close to light speed, its length gets contracted in the direction of its motion. From the spaceship's perspective, the entire universe is moving backward. For us, the universe is contracted along our direction of motion, so the length of the journey to reach our destination is shorter than expected. We are not talking about optical effects anymore but of a physical and concrete phenomenon. If we tried to reach a distant star, the journey would genuinely seem shorter to us. It would take less and less time, the faster we move. Thus, contrary to popular misconception, it is possible to travel thousands of light years in just a few seconds. And in the case where we would move almost at light speed, the journey would even seem instantaneous to us. For the people on Earth, however, several thousand years would have passed. Length contraction is a very real phenomenon. However, visually, it would be difficult to see. To understand why, imagine that we cross the orbit of a planet. As it moves very quickly towards us, the planet's length is contracted. But remember, the farther we look into space, the farther we look into the past. From our perspective, the back of the planet is located further in space than the front. The image that we receive from the back of the planet has taken longer to reach us, so we see it as it was in the past. Even if it is contracted, the planet does not look like it because we receive the image of its back with a delay. Rather than contracted, it appears to be rotated. This is the Terrell-Penrose rotation. When we move very fast and look to our side, the edges of the objects around us seem shorter in the direction of motion. This can be interpreted either as length contraction or as a rotation, a change in perspective. For the same reason, a person watching us zoom by would not really see our ship contracted but rather rotated on itself. Over time, our field of view continues to contract. It intensifies in front of us while going completely black behind us. By accelerating more and more, we might expect to reach the speed of light at some point. What would we see then? This question might be one of the most fundamental in relativity. The answer is no. Even if the ship accelerates constantly, we will never reach the speed of light. That is because the speed of light is absolute. You may try to catch a light ray, but from your point of view, it will always escape at the same speed, the speed of light. You may accelerate as much as you wish. Even if from Earth you seem to approach the speed of light, from your point of view, you are still motionless, and light escapes inexorably. In short, it is strictly impossible to exceed or even reach the speed of light. At best, our ship will continue to accelerate forever, and our field of vision will continue to shrink ever more until forming an infinitely bright spot in front of us, surrounded by a completely black sky. Almost at light speed, all optical effects would become extreme. As we catch up with the light rays before us, they all seem to come from the front. Meanwhile, the rays behind us can never reach us. In our frame of reference, the universe would be extremely contracted, like a thin fabric that we would cross from side to side in a fraction of a second. For a person on Earth, we'd be moving at the speed of light, but for us, the trip seems instantaneous. We move infinitely fast. To conclude, nothing can ever move faster than light through space, but there might be a way to circumvent this rule. In fact, nothing prohibits space itself from moving faster than light. Indeed, the theory of general relativity teaches us that the fabric of spacetime is dynamic. It can bend in multiple ways. We could thus imagine creating a bubble around our spaceship, which we would propel faster than light. This is called a warp drive, in reference to science fiction. It would no longer be a matter of zooming a vehicle through space but of propelling the fabric of space itself. Our ship would remain motionless, surfing on a wave of faster-than-light spacetime. Such a structure may seem absurd, and indeed it is currently thought to be impossible.